Back in a previous section, we used Taylor polynomials to approximations. So, for example, the first degree Taylor polynomial t1 of x was given by f of c plus f prime of c times x minus c. This is like saying you can approximate a function f using a tangent line at the point x equals c. And then the second degree Taylor polynomial was given by f of c plus f prime of c times x minus c plus the second derivative of c over 2 factorial times x minus c squared. And this uses a quadratic to approximate the function f near a point c. We found these coefficients by requiring that the derivatives match at those points. Now you'll find that in general, if f has, and then in the section we just did prior to this one, we found that certain functions, such as like 1 over 1 minus x, can be written as a power series using the fact that this is in the form of some kind of geometric series. Now what this next theorem says that if you have a convergent power series, so if a function f has a convergent power series, it has to have this form. So f of x is equal to a sum that should be from n equals 0 to infinity of a sub n's x minus c to the n, and these a sub n coefficients are the same coefficients that we found using the Taylor polynomials. And if c is equal to 0, this is called a Maclaurin series. So let's find the Maclaurin series for f of x equals e to the x and determine its radius of convergence. So in this case we have c is equal to 0. So we are looking for f of 0 plus f prime of 0 times x plus the second derivative at 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial times x cubed, etc. Now notice for e to the x, the derivative of e to the x is e to the x. So for any n, the nth derivative of e to the x is e to the x, and the nth derivative at 0 is e to the 0 or 1. So this Maclaurin series is actually 1 plus 1x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc., which written in summation notation can be expressed as a sum from n equals 0 to infinity x to the n over n factorial. So that's the Maclaurin series for e to the x. And let's use the ratio test to find the radius of convergence. So we find the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial divided by a sub n, which will be the same thing as multiplying by n factorial over x to the n. Canceling out common factors, we'll have x over n plus 1, and this will equal 0, no matter what x is. Thus, the radius of convergence is infinity. One subtle technical point with Taylor series is that it's not necessarily true that the Taylor series you find has to converge to the function. Like, for example, it's not immediately obvious that we can say that the function f of x is actually equal to that sum from n equals 0 to infinity x to the n over n factorial. Like, so when can we say that this is actually true? Is it true? So what we can kind of think about here is that we can think about the function f of x as being composed of an nth Taylor polynomial plus some remainder. And as long as we can show that the limit as n goes to infinity of that remainder is equal to 0, then that tells us that the limit as n goes to infinity of the Taylor polynomial will have to equal f of x, because as n goes to infinity, this piece will have to go to 0. And to prove that, you're going to need to use Taylor's inequality, which we actually had in the previous section where we discussed Taylor's polynomials. And Taylor's inequality said the following. It said that the absolute value of the remainder is less than or equal to x minus c to the n plus first power, all over n plus 1 factorial, multiplied by the absolute value of the maximum of the n plus first derivative. And we're going to use this to actually show that e to the x does equal its Maclaurin series. So suppose we have, so first of all, we know that the series n equals 0 to infinity x to the n over n factorial converges for all x, and this tells us that the limit as n goes to infinity of x to the n over n factorial is equal to 0 for all x. Remember that if a series converged, the limit of its terms had to be 0. So now we'd like to show that the remainder in this Maclaurin series is going to be to 0. So since f of x is e to the x, the n plus first derivative is also e to the x. Now, given any interval from, say, negative d to d, we'll say including the endpoints, the maximum occurs at x equals d. So we have that the absolute value of the remainder is less than or equal to e to the d over n plus 1 factorial multiplied by x to the n plus 1, as long as the absolute value of x is less than or equal to d. And then taking a limit as n goes to infinity of the expression on the right, e to the d is just some constant, possibly humongous constant, but it is still just a constant. So we'll have e to the d factoring out, taking a limit as n goes to infinity, x to the n plus 1 over n plus 1 factorial, which we discussed up top that this limit has to be 0, so this is equal to 0. And thus we know that e to the x converges to its Maclaurin series for any x. So e to the x is actually equal to the sum from n equals 0 to infinity x to the n over n factorial. In general, I'm not going to make you prove that, but just be aware that there is that technicality. So using the results of example 1, let's find Maclaurin series for some related functions. So recall that e to the x is given by the sum from n equals 0 to infinity x to the n over n factorial. Now, in this example, the function that I have is e to the negative 2x. So instead of inputting x, I can input negative 2x for x. So I'll have a sum from n equals 0 to infinity, negative 2x to the n over n factorial, which can be expressed a lot of different ways. It can be expressed as a sum from n equals 0 to infinity, negative 1 to the n, 2 to the n, x to the n over n factorial. Theoretically, web science should take all different kinds of answers. If they don't, let me know. There's no specific way that I think that it has to be listed to be correct, so as long as your answer is equivalent, I should be able to take it. Alright, here we have e to the x plus e to the negative x. So e to the x will be given by a sum from n equals 0 to infinity, x to the n over n factorial. And e to the x will be given as a sum from n equals 0 to infinity negative x to the n over n factorial. So that's the same thing as 0 to infinity 1 times x to the n over n factorial, plus the sum from n equals 0 to infinity negative 1 to the nth x to the n over n factorial. And combining these into one sum, because both sums are convergent, we can do this. So we'll have 1 plus negative 1 to the n x to the n over n factorial. This is like factoring out your greatest common factor. So in general, the Maclaurin series that you find for e to the x is a good representation near 0. Next, let's find a Taylor series. So this is centered at a different point. In this case, we're centered at a equals 5. So it is still the case that the nth derivative of e to the x is always e to the x. So the general form of a Taylor series is f of c plus f prime of c times x minus c plus the second derivative at c over 2 factorial times x minus c squared, etc. So in this case, f of c will be e to the 5th. F prime of c is also e to the 5th times x minus 5 plus e to the 5th over 2 factorial times x minus 5 squared, etc., which in summation notation is a sum from n equals 0 to infinity e to the 5th x minus 5 to the n over n factorial. Next, let's find the Maclaurin series for another common function, for sine of x. So here the differentiation process is not quite as easy as e to the x, but there is a pretty obvious pattern. So the function we start with is sine x. The derivative of sine is cosine x. The second derivative, so cosine's derivative, is negative sine x. And the third derivative is negative cosine x. And if you were to differentiate negative cosine x, you're going to end up back at sine. So these derivatives are going to cycle in cycles of 4. And then notice that f of 0 is 0, sine of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, and the third derivative at 0 is negative 1. Alright, so we'll have sine of x is equal to the Maclaurin series f of 0 plus f prime of 0 times x plus the second derivative at 0 over 2 factorial x squared plus the third derivative at 0 over 3 factorial times x cubed, etc. So f of 0 is 0, f prime of 0 is 1. The second derivative at 0 is 0. The third derivative is negative 1. Now the fourth derivative will fall into this category, so that will be 0. But the fifth derivative will be 1, so we'll have 1 over 5 factorial x to the 5th. The sixth derivative will be 0, but the seventh derivative will be now going to be negative 1. So we'll have minus 1/7 x to the 7th, or 1 over 7 factorial. So as you can see, what we're getting here are all the odd powers, which, if you remember from pre-calculus, sine is an odd function, so it kind of makes sense that sine should have an odd numbered polynomial expansion. Now how you express that in a summation notation is this. So there are many ways, but this is the most common one. Start from 0 up to infinity, negative 1 to the n. So this ensures your first term is positive because negative 1 to the 0 is 1, and the negative 1 to the first is negative, making the second term negative. Now how you get all odd powers is we're going to have x raised to the power of 2n plus 1. So when you input 0, you get x to the first. Inputting 1, you get x cubed. 2, you get 4 plus 1 is 5. Okay, over 2n plus 1 factorial. I didn't officially prove that this equals sin x, but it is the case that sin x is equal to this Maclaurin series. And the radius of the convergence for this series you can verify with the ratio test, but it is also infinite. So it has interval of convergence minus infinity to infinity. And we're going to use this Maclaurin series to find other Maclaurin series of functions that involve sine. So, for example, x times sine x. We can find the Maclaurin series for this function by taking x multiplied by the series for sine, which was a sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So when that x distributes into the series, we end up with negative 1 to the n, x to the 2n plus 1 times x, over 2n plus 1 factorial, and that's x to the first. Because these bases are the same, those powers add, and I will require that you do combine stuff when it can be combined. So in this case, you'll have to write x to the 2n plus 2 over 2n plus 1 factorial. Now for sine of root x, we can just take our regular Maclaurin series for sine x. So sum n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, and we can input root x. So that's the same thing as sine of x to the 1/2 power, or the sum from n equals 0 to infinity, negative 1 to the n, x to the 1/2 to the power of 2n plus 1, all over 2n plus 1 factorial, which is the same thing as 0 to infinity, negative 1 to the n, x to the n plus 1/2, all over 2n plus 1 factorial. So now that we have a Maclaurin series for sine, we can also find a Maclaurin series for cosine. You could use the same process where you find derivatives and you look for a pattern, and it's not very difficult, but there is a smarter way to do it, a really clever way, is notice that the derivative of sine is equal to cosine. And so if I take and differentiate this series expansion for sine, which was x plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, etc. And I differentiate that term by term, I get 1 minus 1 over 3 factorial times 3x squared plus 1 over 5 factorial times 5x to the 4th minus 1 over 7 factorial times 7x to the 6th, etc. Or 1 minus 1 over 2 factorial x squared, because 3 factorial is 3 times 2 times 1, the 3's can cancel, plus 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th, etc., which is the same thing as the sum from 0 to infinity, once again still negative 1 to the n, x to the 2n over 2n factorial. Of course, as an alternative, one could have just taken this series and differentiated it, not using the expanded form. The power of 2n plus 1 would pull down, so still negative 1 to the n. It's just a constant, but you would have had 2n plus 1 x to the 2n, because you would have taken 1 away from the power, all over 2n plus 1 factorial, and you would just have to notice that 2n plus 1 factorial is 2n plus 1 multiplied by 2n factorial, and you would get the same thing. So next, let's find a Taylor series for sin x centered at x equals pi halves, as opposed to the Maclaurin series, which is centered at 0. So we go back to our previous example, and I will just copy down all of our derivatives. So the function is sin x, the derivative is cosine x, the next derivative is negative sin x, and the third derivative is negative cosine x. And now plugging in pi halves, f of pi halves, so sine of pi halves is 1, f prime of pi halves is 0, the second derivative at pi halves is negative 1, and the third derivative at pi halves is 0. So at pi halves, f of x would equal f of pi halves plus f prime of pi halves times x minus pi over 2 plus the second derivative at pi halves divided by 2 factorial multiplied by x minus pi over 2 squared, etc. So now all of the odd derivatives are 0. So we'll have 1 plus 0 times x minus pi halves, so that part goes away, minus 1 over 2 factorial, x minus pi over 2 squared. The next term will be 0. After this we'll have 1 over 4 factorial, x minus pi halves to the 4th, etc. So written in summation notation, that's a sum from n equals 0 to infinity, negative 1 to the n, x minus pi halves to the 2n power, because we only have even powers, divided by 2n factorial. The final series that you're going to find a final function we're going to find a Maclaurin series for is 1 plus x to the power of k, where k is any real number. So first of all, notice, so f of x is equal to 1 plus x to the k power, and therefore f of 0 is 1. The first derivative is given by k times 1 plus x to the k minus first power. So the first derivative at 0 is k. The second derivative will be k times k minus 1 times 1 plus x to the k minus second. And the second derivative at 0 is k times k minus 1. Now just to see the pattern, let's just do one more derivative. The third derivative is given by k minus 1 multiplied by k minus 2, 1 plus x to the k minus third, and when we input 0, we'll have k times k minus 1 times k minus 2. Now in general, the nth derivative is going to be k times k minus 1, and notice that this last term, so this was the third derivative, this is k minus 2. This was the second derivative, this was k minus 1. So the last term you're going to have in that product is k minus n, and then plus 1. And then the power on the 1 plus x will be 1 plus x to the k minus n, and the nth derivative at 0 will be given by k minus 1 multiplied down to k minus n plus 1. So that tells us that our Taylor series for f of x is 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed etc. This one is often best if you just list the terms out. I won't explicitly ask you to put them into summation notation. And in your textbook, you can verify that for this series, the radius of convergence is r equal to 1. The interval of convergence can vary based on what the value of k is. Alright, so let's find the Maclaurin series using that formula we just derived. This is the same thing as 1 plus x to the power of 1/3. So we're going to apply the previous formula, and we will use k equals 1/3. So just to have it written down on this slide, recall that f of x for this k will equal 1 plus kx plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 all over 3 factorial times x cubed, etc. And if I ask you to do this on a quiz or a test, I will specify how many terms I want from you. I'll say list the first 5 or 6 terms. 1, 2, 3. In this case, we're just going to do the first 5. So 1 plus 1/3 x plus 1/3 times 1/3 minus 1, all divided by 2 factorial, x squared, plus 1/3 times 1/3 minus 1 times 1/3 minus 2 over 3 factorial x cubed, and then plus 1/3, 1/3 minus 1, 1/3 minus 2. We'll just stop at x to the third since I don't have any space. Alright, so etc. So 1 plus 1/3 x. Now 1/3 minus 1 is negative 2/3. So we'll have 1/3 times negative 2/3 over 2 factorial x squared plus 1/3 times negative 2/3 times, so 1/3 minus 2, 2 is 6/3, so negative 5/3, 3 factorial x cubed, etc. So that's 1 plus 1/3 x. Now minus 2 over 3 squared times 2 factorial. One kind of tricky kicker is that this 2 factorial, to get that out of the denominator, you multiply by 1 over 2 factorial, 1 over 2 factorial. These cancel, and this 2 factorial is actually in the denominator. Times x squared. Next we'll have plus 2 times 5 over 3 to the third times 3 factorial x cubed. It's occasionally better to keep things not multiplied so you can kind of see the patterns that are going on, because based on these patterns you can probably surmise what the next term is going to be. Ignoring these first 2 terms, everything's going to be alternating, so my next term is going to be negative. And we'll still have 2 times 5, and it looks like these numbers are 3 spaces apart, so the next number should be 8. The powers on the 3's match the powers in the variables, so we'll have a 3 to the 4th times 4 factorial x to the 4th, etc. So roughly speaking, that's the start of the Maclaurin series for 1 plus x to the power of 1/3. Those are pretty darn ugly, and I think there probably is a way to write it in closed form. There is not a very easy way to write it in closed form.